Good morning to all. Now we are going to see anthropogenic activity of CO2 emission. What is anthropogenic activity? Anthropogenic activity is nothing but activity caused by humans which relates to CO2 emission. Starting with road transportation, globally one-third of air pollution is caused by road transportation. But this road transportation is unavoidable because the entire growth of a nation is depending upon the road transportation, and this is a good better choice for industrialization. This industrialization, that means transportation, is directly depending upon fossil-based fuels, which is an IC engines and fossil-based fuels or petrol and diesel. Even in this electric vehicle era, by 2040, the half of transportation will be still operated by fossil-based fuel. That tabulation clearly shows that the various pollutants which is emitted by IC engines were consuming fossil-based fuel, starting with oxides of carbon, which is maximum by its volume, which is 740%, oxides of nitrogen, which is 20%, oxides of sulfur, which is 1.5%, hydrocarbon is 24%, organic acid 1.4, and particulate matter is 2%. Going to the statistical data, even if we change the entire fossil-based fuel, which is an IC engines, to an electric vehicle, there is nothing called zero emission vehicle. The only thing we are transferring the footprint of CO2 emission to other mode of emissions during the manufacturing of electricity. This increase in urbanization and population creates creates demands and on power generation. Globally, major sources of production of electricity are coal and natural gas. This is almost 61.4% by its volume. This graph clearly shows that maximum consumption of for electricity is depending upon fossil-based fuel, and there is a fluctuation in nuclear, hydro, and wind biomass and solar energy. But the maximum consumption is done on fossil-based fuel. This huge consumption of fossil-based fuel, starting from lignite, or coal, oil, natural gas turbine cycle, emits tons and tons of CO2 into the atmosphere, which is maximum by its volume, and this should be monitored to rectify the depleting air quality index. The carbon cycle of concrete, starting the cycle of concrete. The concrete is the second most consumable material in the world, stands next to water. This consumption literally discharges tons and tons of construction demolition waste as a landfill and affect the agricultural land and a country, which is India is an agriculture based country. The environmental impact caused by construction demolition waste are land space consumption, landfill depletion, energy and non-energy resource consumption, resource depletion, air pollution, noise pollution, and water pollution, etc. This, on the other hand, the rapid administration continued to accommodate more number of people in urban infrastructure, which is almost 3.5% people live in cities and almost 70% of the entire world population are urban settled by 2050, which is reflected by Human Development Index, is directly correlated with the material footprint, assuming the similar system of production 9 billion peoples and consumes 180 billion tons of material annually by 2050. This chart shows that generation of construction demolition waste in million tons per year, and which is maximally contributing country is China. Continuing to carbon cycle of concrete, starting with the manufacturing of cement. This is a key source of CO2 emissions, starting with the manufacturing of cement, which is calcination. This is the chemical reaction that occurs when limestone calcium carbonate is heated to produce calcium oxide, that release CO2. This step contribute 50 to 60% of total emission from cement manufacturing, which is a CaCO3 equal to CaO plus CO2. The fuel consumption, going to the fuel consumption to react the high temperature required in the kiln around 1450 degrees Celsius. Fossil fuel like coal, gas, petroleum coke are burned, contributing to 30 to 40% of CO2 emissions. And going to electricity usage, using a grinding raw material and cement clinker, this contribute around 5 to 10% of emissions depending on energy sources. The total emissions of cement production typically generates around 0.7 to 1 ton of CO2 per ton of cement. The mitigating process which we are accommodating is that we can use the biomass to increase the kiln efficiency, incorporating supplementary cementitious material like fly ash, slag, to reduce resilience of a clinker. Going to the mining of aggregate, the key sources of CO2 emission during mining of aggregate are extraction, heavy machinery such as excavators, trucks running on diesel are used for extraction and transport aggregate, leading to significant emissions. First thing, after extraction, aggregate were washed, crushed, and sorted using energy-intensive process, often powered by fossil fuel. Transportation of aggregate are transported from mining site to batching plant, generating additional emission depending on the distance traveled and the fuel used by transport vehicle. This total emission is lower than cement manufacture, but aggregate mining still contribute to notable CO2 emissions due to energy use and transportation. Going to the concrete batching. Concrete batching is a process of mixing cement, water, aggregate, and mixture to create concrete. While less carbon intensive than cement production, batching still contributes to CO2 emissions. The key sources of CO2 emissions are cement content. CO2 emission in this phase depend largely on amount of cement in the mix. The cement typically account 90% of carbon footprint of the concrete, as discussed inner and external cement. Energy use, batching plant use electricity to run mixers, conveyors, and other machineries with emissions depending on electricity sources. Water usage, minimal emission, but it is colder climate, heating water for batching can slightly increase the carbon footprint. Transportation of material to the batching plant also add to the overall emissions. Total emission is around 300 to 500 kg of CO2 per cubic meter, largely due to the cement content. Going to the transit of cement content to the site, the overview shows that transportation of concrete from batching plant to the construction site is largely solved by CO2 emission. The key sources of CO2 emissions are truck emission. Concrete is transported in a mixture truck, usually powered by diesel, which generates CO2 based on distance and size of a load. Traffic and idle time. Traffic delay and idle time can increase the fuel consumption. Further rise emission. The longer the transportation distance, the higher the emission. Choosing batching plant closer to the construction site reduce the impact. Then we are going for the construction. CO2 emission during construction practices overview. On-site construction activity contribute to CO2 emissions through energy use, machineries, operation and material handling. Key sources of CO2 are machinery equipment, excavators, cranes, bulldozers, and other heavy machineries are typically powered by producing significant CO2 emissions. On-site energy usage or generator and construction site lighting consume energy often from fossil fuel, adding to the emission. Material handling, cutting, shaping material, particularly energy intensive one like steel, concrete, add to the emission. The mitigating strategies are using energy efficiency and machineries. Then the CO2 emission during maintenance and repair is an overview shows that maintenance phase of a building life cycle also contributes to CO2 emissions, typically less than construction phase. The key sources are energy use, routine maintenance, example, lighting, repairs, consume energy over building lifespan, producing CO2 based on energy source. Material uses are repairs that involve replacing materials such as a concrete, steel, or glass, incur additional emissions from the production and transportation of these materials after the end of life. The demolition based overview of at the end of building life, demolition produces significant CO2 emission primarily due to energy used to waste disposal. The key sources of CO2 of demolition machinery is heavy machineries like drinking bowl, excavator, crusher run on diesel, producing substantial emission of CO2 into the atmosphere. Transportation of waste is demolition debris is transported to recycling facilities or landfill, contributing to CO2 emission based on distance fuel consumption. Waste processing include recycling concrete, steel requires a crushing, sorting, reproduction, but produce fewer emission compared to sending waste to the land. And CO2 emission from landfill around is an overview which an addition of CO2 and methane emission are generated over time. The key sources are transportation and handling. The transportation waste to landfill and compacting it generates CO2 directly into the atmosphere. Decomposition of organic material like wood, other organic metals in landfill decompose anaerobic releasing methane, which is a greenhouse gas 250 times more potential than CO2. This entire cycle is directly or indirectly emits CO2 into the atmosphere, which include recycling as discussed earlier. Now we are going to carbon uptake cycle of concrete by utilizing construction demolition waste aggregate in a concrete. This construction demolition waste is big in strength because it is already constructed and they are demolished, and it has an highly porous membrane, which is cement mortar, which leads to depletion, degradation in their strength, and are not suitable for an load bearing structures. So they has to be reconditioned and retreated with a chemical or adsorbent to increase their pore structure and CO2 uptake by a process of carbonation. This modified construction demolition aggregate can be an enhanced surface structure, which shows enhanced microstructure by due to the pores are filled by adsorbent, and this adsorbent directly reacts with CO2 to form carbonates of calcium and other things, which include during which they uptake CO2 during their calcination carbonation process. And this carbonation process enhances strength parameter of modified construction demolition waste. This modified construction demolition waste can be a replacement for natural aggregate during concrete manufacture that reduce the sustainability, and this entire cycle is carbon uptake cycle of an concrete while we use demolition waste aggregate as an replacement of natural aggregate in a concrete, which paves the way for sustainable growth of an construction industries and which is considerably economical when compared to utilization of natural aggregate in the manufacturing of concrete. To bridge a gap between material wastage and material shortage, the recycling of waste material is the only solution. We come out with a feasible solution by combining with adsorbent, which is a chemical which has capability to absorb CO2 directly from the atmosphere, and they are available in a polymer form which can be diluted in water at various concentrations to find the optimum percentage that gives a maximum pore filling ability and CO2 uptake, and they are combined with construction demolition waste, which is highly porous. The pre-treatment and precondition is done in a way that the adsorbent is mixed with an potable water at a varying percentage, and the construction demolition waste is added. They are periodically mixed to include that adsorbent completely dissipate into the pores of a construction demolition, and this concentration will be varying depending upon the utilization. And this non-treated construction demolition waste should be heated in a oven around 60 degrees Celsius, because normally we'll heat it around 100 degrees Celsius. During the 100 degrees Celsius heating, the chemical composition there's a possibility to break down, and it will not form the required chemical product while combining with adsorbent and CO2. This modified, treated, preconditioned construction demolition waste undergoes CO2 uptake by a process of carbonation in a carbonation chamber. After carbonation, this adsorbent modified construction demolition waste shows the complete complete pore filling ability and the surface structure enhanced by undulated project plate-like formation, which enhance the bindings and the bond strength between the concrete and the cement matrix. This modified construction demolition based shows enhanced microstructure, which increase CO2 uptake and cell parameter, which can be the replacement of construction demolition waste, which can be replacement of natural aggregate, and this construction demolition waste can be utilized in a product. Now we are going to see life cycle of reverse osmosis, starting with the drinking water. Good morning to all. Now we are going to see life cycle of reverse osmosis membrane reduced line, starting with the drinking water. Globally, there are 3% of available fresh water, in which 2.5% is frozen. The water is essential for life, yet we have only 1% of fresh water on Earth, rest being locked in glaciers as discussed. The limited availability of clean water creates a global crisis, especially water scarce regions. Historically, societies settled around abundant water sources, but the population growth urbanities. The demand of clean water outstripped the supply, leading to global water price scarcity. Owing to the population growth, the world has currently 7.9 billion and India is 1.38, after China it is 1.25 million. The statistical data in 1950 it was 2.5 billion and 2020 it was 1.8 billion and 2050 it will be around greater than 11.6 billion, which keep on increasing, which is due to urbanization, industrialization, through standard further increase the demand of demand and scarcity of drinking water. Globally, water usage grew by 1% per year, driving largely by increased demand in developing national industrial urban centers. The freshwater availability and pollution, not only the freshwater limited by also human dispute. About half of world population already live in area facing severe water crisis, especially in regions like Middle East, North America, and parts of Asia. Pollution is a key factor in reducing availability of water. Chemical runoff from agriculture, industrial waste, and untreated sewage contaminate local water sources, making them unsafe for human consumption and adding further pressure on water treatment technology. The population growth, the statistics. According to UN Department of Economic and Social Affairs, the world population is expected to be greater than 1.6 billion. The water scarcity is that 2.2 billion people do not have access to safe drinking water. Approximately 4 billion people experience water scarcity at less 1 month per year. The freshwater withdrawal use. The global water withdrawal is divided between agriculture, industries, and domestic. Agriculture, particularly irrigation, is largest consumer and the population growth demand of water for food production will increase. Industrial activity such as manufacturing, mining, power generation also consumes a significant volume of water, intensifying the station on available freshwater resources. Domestic demands, especially in urban areas, will expect to rise sharply as an administration. And this global water crisis hotspot on India and China. Together, these two countries account for 36% of global population and both are facing severe groundwater depletion. India 21 cities are expected to run out of groundwater by 2030, affecting over 100 million people. Middle East, North Africa region already suffer from extreme water scarcity, with many countries relying heavily on desalination to improve their water. And Sub-Sahara South Africa water scarcity combined with the poor infrastructure, which in some countries less than 40% of people has access to clean water. This demand affordable water with respect to income groups or access disparity. Access to clean water, potable water is often determined by income level and sub-economical factors. In wealthier countries and communities, advanced technologies like RO systems provide safe water, whereas poor regions struggles with access to even basic water resources. The higher income group, which is HIG, as per the qualifications, they need 200 liters per day. The access to advanced water treatment technology is done with an HIG. The water wealthy household, particularly in urban area, often use homemade reverse osmosis systems and municipal water treatment facilities. This ensures a constant supply of clean, safe water for drinking, cooking, and even non-essential activities like gardening and car washing. The consumption pattern of wealthier population consumes significantly more water per capita. In high-income group countries like United States, the average people use 304 liters per day, and compared which is less than 50 liters per day in low-income countries. This disparity increases the environmental burden and strain on local water resources. Coming to local and low-income group, LAG, which has 135 liters per day as per the International Foods. They have limited access to potable water. Low-income countries, particularly in rural areas, people often rely on untreated water sources such as rivers, lakes, and shallow wells, which may be contaminated with pathogens or pollutants. This leads to widespread health problems like diarrhea, cholera, dysentery, and especially in children. The affordability issue for many purchasing a clean water is prohibitively expensive. In some areas, people spend up to 10% of their income on water. It is difficult for families to meet other essential needs. The public health impact of water disparity, the lack leads to lack of access to potable water, major cause of morbidity and mortality, leading particularly among children and the poor sanitation. 4,85,000 deaths annually due to diarrhea. Economic impact leads to the lack of clean water has significant consequence, especially in lower income. It leads to lost productivity, healthcare costs, resources, education, and opportunity in two places. Women and children bear a each time for school. And going to the statistics, the requirement of water per day for India is 600 is 1,200 million. This can be achieved with an implement and using a filtration of RO. What is RO? Reverse RO. It's a reverse osmosis. A water purification technology that removes impurities from water by applying pressure, force it through a semi-permeable membrane which blocks salts, chemicals, bacteria, and other contaminants. It is widely used in household industries and desalination plants to produce drinkable water. The structure of RO membrane are typically made of thin film composite material consist of polyamide layer or porous polysulfide substrate. The polyamide layer allows the water to pass through while rejecting contaminants because of size and charge. These membranes are highly selective, capable of filtering out a particle as small as 0.1 nanometer, which include bacteria, virus, and dissolved salts. The filtration capacity of an RO membrane is highly effective at removing contaminants. They typically remove 95 to 99% of dissolved salt along with bacteria, virus, pesticides, heavy metals such as leads and arsenic. Application RO membrane are used in a wide variety of applications, including household water filtrations, common in urban area. RO system provide a clean drinking water by filtering tap water. Industrial use RO is used in industries like pharmaceutical, food processing, electronic, where ultra pure water is offered. And desalination units, these are crucial for converting seawater into potable water in arid regions. Limited freshwater and water recovery efficiency of RO membrane is 50 to 70 percentage of treated water, meaning that 30 to 50 percentage is lost as water wastewater, which contain high concentration of salt and other contaminants. In desalination plants, the water recovery rate is often lower due to high salt content of seawater and require higher energy input and generating large volume of brine. The desalination and role of oil, global use desalination have 30 million people worldwide, particular region like Middle East. The energy demand of desalination is very high, it is 3 to 6 kilowatt of electricity per cubic meter of water produced. The advances of RO technology in recent years and membrane technology has improved energy efficiency of RO systems, reducing their environmental impact. Low energy membrane and forward osmosis system and are developed to reduce energy consumption, desalination. There is a desalination using a mildew which gives to the requirement of water scarcity or tenacity, which is around 100 milliliter, which is around 100 milliliter. The CO previous will be around 40,000 to 60,000, which leads to higher discard of used RO membrane in and around the plant, which is around a rough of 120 liters per day. The waste generation leads to an RO membrane lifespan typically lasts 3 to 7 years, depending on water quality, pressure condition. After this period, they lose efficiency due to fouling, scaling, and they are often discarded. With millions of RO systems operating worldwide, the number of discarded membranes will keep on increasing. It is estimated that thousands of tons of RO membranes are discarded each year, contributing to the plastic waste. And second one is that they accumulate as a non-biodegradable landfill. RO membrane are primarily made from polyamide as discussed, a synthetic polymer that are non-biodegradable. This means this discarded membrane can reside in the environment for hundreds of years, contributing to the growth of problem of plastic pollution in land. As a landfiller, the improper disposal of used RO membrane can result in leachate, a liquid formed when rainwater filters through the waste and create toxic chemicals into the soil and groundwater. The potential toxicity of used RO membrane, in addition to the membrane that makes up RO membrane used membrane every time, contaminant from water they filter, including heavy metals, pesticides, and industrial chemicals. These contaminants could lead out to over time poses a risk of soil and groundwater quality, especially in areas where landfills are not properly maintained. The environmental risk associated with the disposal of used RO membrane highlights the need for better waste management practices, recycling solutions, contributing to the global water management problem. The improper disposal of RO membrane contributes to broader issues of plastic waste. With the growing use of desalination plants, the household RO system, and the volume of discarded membrane is expected to rise exponentially, exacerbating the global water crisis. Additionally, the production of new RO membrane requires significant energy and raw material adapting to environmental footprint of other technology. Going to the feasible solution is to recycle the RO membrane is the repurposing and secondary applications. Reuse in wastewater treatment. One solution is repurposing discarded RO membrane for less demanding applications such as treating industrial waste or agricultural. These applications provide the same level of filtration efficiency, allowing membrane to be reused even after their efficiency for potable water is decreased. Pilot product. Several researchers produced reusing of RO membrane for grey water recycling, helping to reduce the demanding for new membrane and elevate the water disposal issue. These systems are being tested in various industries, including textile manufacturing, physical and chemical recycling. This physical recycling process involves cleaning and refurbishing membrane for continued use. Membrane can be mechanically cleaned to remove scaling and fouling, then reused in applications like industrial waste treatment and aquaculture. Chemical recycling is more advanced method involves chemically breaking down hollow membrane into their base material. For example, polymer layer can be broken into monomer and reused to produce a new membrane. Although this process is not yet widely adapted to its cost and complexity, ongoing research is focused on making And bio-based, biodegradable membrane is that researchers are developing membranes that are made from bio-based chemicals which could reduce their environmental impact. These membranes designed to be more sustainable with the potential of biodegradability once they reach the end of life. While still in development, bio-based membrane could revolutionize the water purification industry by addressing both waste. Industries and government initiatives is done with circular economy model. Circular economy approach involves creating a closed loop system where recycle, reuse, reducing waste and this context. Auto membrane could be recycled into new and repurposed for secondary application, minimizing their disposal in waste. Extended producer responsibility is applied, which is an EPR. A government can implement policies that require manufacturers to take responsibility for the disposal of recycling of their producers. This concept known as extended producer responsibility stripped off the burden of waste management from consumers to producers, encouraging the development of more sustainable produce design and recycle programs. An energy efficient alternative to automobile are forward osmosis and computation alternative water treatment technology like forward osmosis and is exposed as energy efficient alternative to automobile. Those methods require less energy and could potentially reduce the environmental footprint of water purification while also addressing the waste management issue associated with automobile. Next is the public awareness and policy advocacy. Raising public awareness, encouraging consumers to be more aware of environmental can lead to greater demand for recycling programs, education can elevate the environment. Government policymakers can promote adoption of sustainable. Finally, the conclusion the key points. Global population is up 21st a crucial role in this challenge, providing fundamental especially in the. However, growing uses of RO system rise significantly as with respect to disposal of used membrane which contribute to plastic pollution. Ensure that RO technology is crucial for recycling, repurposing, development, biodegradable, using part is the role of innovation, development of low energy and replace be a key to make purification more sustainable. Use recycling sustainable to mitigate the environmental impact while promising circular that looking ahead of further application as demand for efficiency sustainable technologies indicates significant advancement in efficiency research collaborative and where collaboration future generation. Final thought is that perfection usual business. Similar person, supporting